in 4.1, looking at finding sums of infinite limits. So we saw from the last video, just looking at area underneath the curve here. So we got this curve, it's probably y. It's y equals x squared plus 1. That's the equation here. So before we did left-handed, right-handed, like based on how many rectangles we have. So here we can see our n equals 6. So we would take 2 minus 0 and divide that by 6. And so we get 1/3. So we can see that these are 1/3 distances, each of them 1/3. And then depending if we go from the left-hand side of 6, we'd go from the left 1/3. So that would be this one. So I'm going to use this x one here, which is 1/3. And then 2/3 x, 3/3, 4/3, 5/3 x. And the left-hand side, oh, sorry, that's right-hand side. So if we do right 6, we would do 1/3, 2/3, 3/3, 4/3, 5/3, and 6/3, which is 2. Right? And so those would be all the right-hand side ones. And then we would add up we'd plug in those values, 1/3, into our equation to find out what the y values are. And then we can add up all these y values right here. So 1, 2, 3, 4, 5, and 6. And then just times it by 1/3 our width of the rectangles, the width. Right? And then, or we have the left-hand side. So we have the left-hand side somewhere in here. So left-hand side might look something like this. So they're all below. Again, I would use these values, right? So I might use the first one. I think our graph kind of got shifted over here. There we go. And so the left-hand side, start right here at 1 and move over from there. So 1, then this one at 1/3. So 0, 1/3, 2/3, 3/3, 3/3, 4/3, and 5/3. So those would be the x's that I use to plug in order to get my y's. And then I would add each of those y values right here. So this y value 1, 2, 3, 4, 5, 6, and then times it by my width, which is 1/3. So that would be the left hand of 6. And then the midpoint or middle, I would have to find the middle of these x's, 1/4, find the middle of these two x's, and plug those values in order to find this y value for the midpoint, right? And then our equation looks something like this. We had the one problem just plain y equals x squared, and I think from the left 4 was our width was 1/2, and then we had 0, 1/4 plus, I'm adding here, plus 1 plus 9/2. So as we can increase our n, as we start increasing our n, we saw that, and I'll show you here again, as I increase my n, we can see that the gap in between here, right here, starts getting smaller and smaller and smaller. So we really get closer to that area. Here I only can go up to 15, but we saw in the one video that that's shrunk. So if we increase this, if we just take the limits of these, as n increases increases to infinity, then we're going to get truer and truer to whatever this area is going to be. Right? So as we take the limit as n goes to infinity of these, then those are going to increase and increase and increase. Well, instead of continually adding, right, because I had to do 0 plus 1/4 plus 1 plus 9/2 plus blah 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 blah. So this guy named Raymond, or last name Raymond, something like that, he came up with this kind of notation that you can write. And so here's looking at the limit as n increases without bound, or goes towards infinity. And we get this notation, this sigma notation somewhere in here. There we go. This sigma notation. And so this is the summation sign, means add it up, right? And we start with I. So that's plugging in, that's for like 1 rectangle, 2 rectangles, 3 rectangles, all the way up to n rectangles that we're adding. M just stands for the number that we're starting off. Usually you can start with 0 or with 1. Most of the times we'll see it starts with 1. And we just keep on going until how many rectangles we're doing, right? But since if we're going on to infinity, this would just stay at 1. And we did at least one example of this. And so that's how we kind of see the different notation. So we have the sum sign, means we add up. This is our y values that we're adding up. Here's our change in x. It's the b minus a all over n. So that's the width of our rectangles. So the width of our subintervals, or width of our rectangles, this f of xi is all our y values, and then it's telling us to sum those up, starting with the first rectangle and going all the way to however many n rectangles we have. So start, finish, telling us to add all the y values, and then multiplying by our width. That's what this sum notation is telling us, and so it's called the Raman sum. It's after the guy that came up with it. And so we can go ahead and look at, and we did this kind of in class, how this kind of looks. If we were trying to add up, the first numbers, so if we're just continually summing these up, so the first I numbers, so the sum starting with the first number and continuing on to n of I. So if we're adding these up, it'd be 1 plus 2 plus 3 plus 4 plus ... all the way to n. And so what does that come? Is there any kind of formula that can explain this? And so we kind of did this in class, and what we did was we kind of just worked backwards. And we did a couple examples where we actually just add the first 10 numbers, add the first 15 numbers. And so we add up all the first n numbers, and then, so that's a equals s, okay? And then we just do that again, except for we go backwards. This would be 1, the next one would go down and continue on until this one would be, this would be n. So this would be n minus 1, this would be n minus 2, this would be n minus 3, and so on, right? And then all the way down. So if we add these up, we can see this has just become n plus 1. So all these are n plus 1. And I have 2 of them, so I have 2 s's, and this is just n plus 1, and it's all the way. We have how many of these n plus 1s? N plus n plus 1. Don't I have n of them? Because there's 1, 2, 3, 4, all the way to n. So I have n amount these. So that means this is just n times n plus 1, and divide that by 2. So that means our sum of the first however many numbers I want to go to is n times n plus 1 all over 2. And so that's the sum of this. And you can work through to find this one as well. The sum starting at 1 to n of I squared. And so we did this one in class 2. And we saw that this one was just n times n plus 1 times 2n plus 1 all over 6. And then the third one, if we do a cubed, the sum of a cubed is equal to n times n plus 1, all over 2, and that quantity is being squared. And then we went through some sum rules that said, hey, if we have a sum of ai plus bi, we can just separate that to the sum of ai plus the sum of bi. Same thing with the subtraction. If we have a constant, so we have sum of them constant, we can just pull that constant out and multiply it by the sum of that variable. So we add the variable and then times it by k. And then we said also that if we are just have the sum of a constant, that just equals n times that constant, because we start out at 1 and we go to n, right? So the sum of 3 would be, so the sum starting at 1, say to 4, the constant 3 is just adding 3 4 times, right? So isn't that just 4 times 3? It's 12, right? So we have these kind of properties, well, these properties, and then these sums. The first I numbers, the first I squared numbers, I cubed numbers. So, and we'll go ahead and use those kind of throughout. So these aren't too bad. Like if we start at 1 and go to 4 of our equation, x squared plus 1, that was there. Right, so then we would just plug in, start with 1, plug in 1, square, add 1, right, that's our y value, and then we would add the next y value, plug in 2, so 2 squared plus 1, and you keep on going until you add to the fourth, right, so 3 squared plus 1, and then we would add 4 squared plus 1, so we'd do it 4 times. And so then you just add those answers up. All right, so pretty self-explanatory on there. You could separate this into the sum of I equals 1 to the fourth of x squared, and then we could just add, because we're using this sum property here, the sum of I to 1, starting at 1 going to n of the constant, and remember that constant, that's just n times k, so that's just n times, well, I guess we started at 4, we ended at 4. So 4 times 1 is 4, so this is just 4 plus the sum of this one, the first 4 numbers, right? Which there, this x in this notation, this x squared, this is our function x squared, that's just the same as this function right here. This I just stands for what number you're dealing with, the first x, the second x, and so on. So that xi is used in there. So really this is the same written like this, of f of x I, starting at 1 to 4. So depending on what function you have, that's what's going to go in there, right? So ours is squared, so it's same thing as I squared, right? Because x is being squared, we're just substituting I for x. And so then we do have this equation as well, right? N times n plus. So this is the kind of different notation. So instead of doing it all out like this, we can do it this way. We can use that property there to simplify that constant, pull apart that addition, and then we can simplify this by using the formula of this, right? So then we can go ahead and substitute, and our n is 4, so we have 4 plus 4 plus times 4 plus 1 all over 2, so that's 5, so that's 20, it's 10, so this is going to equal 14. And we can see here that if we add this up, use the wrong formula here, this is and then times by 2n plus 1 over 6. Sorry, that's I squared formula. So switch that. So then we can plug in our n here. So that's 4 times 5 times 9. So 4 times 5 is 20 times 9. It's 180, right? Divided by 6, that's 30. So this is actually equal to 34. And we can see that here. We got 2. We got 5. So that's 7. 17, 24, 24 plus 10 is 34. So we can see that does equal that. So it's easier to use these properties like this than do them one at a time, especially if you increase this n really, really big. All right, so there's an explanation of the sigma notation and using Raymond sums. And so that's kind of the rest of 4.1.